Right. So, welcome all of you again to another experiment for the lab CL801. What we are wanting to do today? We are wanting to do an experiment called TCSPC, right? TCSPC, right? Time correlated single photon count, right? Time correlated single photon count, right? So this is the method what we are going to do today, right? Now what is this all about? It's all about fluorescence, okay, fluorescence. Now what to understand about the fluorescence? What is the fluorescence? Can I rub this? Yes. What is fluorescence, right? So if we know the transition, so there is ground state energy level, then you have the excited state energy level, right? So they are further subdivided into vibronic levels, correct? So how do you draw the ground state energy level? Like this. And they are further subdivided into vibronic levels, right? Vibration levels. And each vibration level is further subdivided into rotational levels, right? Now if let's say I am having the electron here and I am going to excite it here, right? So if if we are talking of the electron which is in the downward spin, will it go up and make the upward spin? Why not? It's not spin allowed. So it has to maintain its spin, right? It has to maintain its spin. So if it goes to any of the excited level, including any of the vibronic levels, and if it comes back, it's a UV visible, right? Electronic transition. But instead, if it goes up and it tumbles down to, let's say, this level, the lowest vibronic level of the excited state, right? And can we measure this? The tumbling down, it's a non-radiative, so you cannot measure it. It is lost forever, right? So now let's say to go up, it has absorbed 100 packets, right? But when it comes down like this, will it liberate 100 packets, more or less? Less, yes. So let's say it liberates 80 packets. So you are having a wavelength and this is the wavelength 2. So this is like, or say wavelength absorbed, and this is the wavelength emitted. Now will my wavelength emitted be of a higher wavelength or shorter wavelength? Higher, because it's lower in energy, right? It's lower in energy. So that's your fluorescence. But instead, if there is an inter-system crossover, right? Now instead of this singlet, you can have the two kinds of transition. One is it goes and maintains the spin, or it goes and becomes a triplet state, right, which is more stable. This is like your phosphorescence, right? Now the fluorescence takes place in the order of 10 to 500 picoseconds, right? Sorry, not picoseconds, nanoseconds. My apologies. 10 to 500 nanoseconds. That range where the fluorescence works, right? This is the order where the fluorescence is working. Now this nanosecond significance, we are going to do one small experiment, right? One small experiment, and then based on that experiment we will try to understand the relevance of TCSPC. You had done lots of fluorescence experiment. So what you had done in that fluorescence, you excite and then you see the emission. Yeah, you see the emission. Is this the same thing what we are going to see in TCSPC? The answer is no. Right? The answer is no. You just see the emission. You just see the emission, but you don't trace the profile of decay. Right? So, any spectroscopy, how does it work? You have the system which is in the stable ground state and then you excite it, right? You excite it and then you cut off your emission, absorption, right? So, does it want to stay in that excited state provided there is no energy? No, it wants to come back to the ground state, right? So, all you are seeing in fluorescence, fluorescence experiment, that you are seeing what happens when you excite and what happens when you stop the absorption or you cut off your radiation, right? But then once it is coming back, the profile of the decay is not what you are measuring in fluorescence. You are just seeing what is happening to the intensity, how my intensity is coming back, right? But then how that intensity is coming back, that profile tracing is not happening, right? I would really like to see the profile, how the fluorescence is happening. Now, if I am saying my fluorescence, the total excitation emission happens in the nanosecond level, it's too quick, right? It's too quick. Now, what I can do, if I have to have a statistically relevant data, what do I need? I need multiple measurements, right? So, how the profile is going back, right? Pretty much like if you are sitting in this admin block, what is your trace to go back to the hostel? Whether you go this way or whether you go from the back side or whether you go all the way around and then you reach the hostel, I don't know. For me to be able to say with any confidence, I really need to measure a lot of your traces. So, what is the most popular way? Let's say Karthik goes back to the hostel in a particular fashion, or he takes a particular route of his choice. For that, I have to observe him for a long time, right? Now, there are two ways of doing things, right? So, I have some coins here. We are going to do one experiment, and for today's experiment, Sonali is going to be our detector, right? So, she has to be very quick with her reflexes. Right, if things goes very wrong, then our detector is quite bad, right? So, we can't be able to tell all the stuff, and for doing that, I want all of you on this bench, right? So, Rupesh, if you can come on this side. A very simple and funful experiment. You come on this side. Yeah. So, Sonali, you stand on this side. So, we need 7 people including myself, right? So, I have 7 coins here. So, I am putting heads up for all of them. That is for you, Gayatri, Karthik, Ashish, then you Pankaj, and then Priyanshu, and where is Hemant is not there, so we need Sandesh. It is his coin, right? So, very simple experiment, we flip it just like that. No, you don't flip it this way, you just flip it like this, keeping your hand on the table all the time, good for the camera, right? She is our detector, so she is going to tell us how many heads, how many tails. Simple, no rocket science, good. Start kare? Everybody can take your coin just like that. Heads up, all of you. Put it down, Sandesh, on the table. Put your hand on the table. On count of 3, you will just flip. And Sonali is going to tell how many heads, how many tails. There are 7 coins. Okay? 1, 2, 3.
Five heads and 2 tails.
5 heads, 2 tails, right? One more time. All heads up. 1, 2, 3, flip.
5 heads, 2 tails.
5 heads, 2 tails, right? So now let's see our detector is sensitive or not, right? So the minute I say take back the coin, you have to quickly take back the coin, huh? 1, 2, 3, flip. Take back the coin. How many heads, how many tails?
I saw 4 heads.
So sensitivity is gone. See, the problem here is if any happening of the event is too quick, we might not be able to see it properly, right? So for statistically relevant data, I am working with high concentration right now, right? We have more coins right now. So then the point here is like all of those are happening at the level of nanoseconds, right? Nanosecond. So detector goes crazy, right? All the decay profile, how I'm going to do, right? That's what happens to my detector, gone, right? So my detector is gone. But instead, what I can do, I can have one coin in my hand and then I keep asking, how much? Head, tails, you have to, huh? You have to keep saying head or tail.
Head.
Huh.
Head.
Oh, jaan do. What is it?
Tail. Head. 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 Head.
Even if I am doing this fast, I am measuring only one particle. So the same statistical relevance I will get if I am measuring one particle million times, or am I doing the million particles in one go? Both of them will give you a similar kind of statistical relevance, right? But practically measuring million in a small span of time is not possible. It's very difficult, right? So how I would like to do single photon counter. Do you understand the relevance of that SPC? Yeah, time correlated. As a function of time, so time is extremely important. If my detector sensitivity is like, very small, or say even if it's very high, am I able to measure events at the level of say nanoseconds? Nanoseconds is very small event. Right? For phosphorescence, I don't bother. It can be minutes to hours. So I'm okay. Yeah, you won't be required to, you can easily see the trajectory profile even using your simple fluorimeter, right? But then to trace the decay profile in the order of nanoseconds, we need something different setup, and that setup is what? TCSPC, time correlated single photon counter. So we are seeing one photon and then trying to see its decay profile. Yeah. Now everybody can take your own respective coins. So I had 3.
So that,
Where is one more gone? Yeah, I need one more. Yes.
so that count will be in that nanosecond
Yes.
for one photon.
The decay profile, the entire decay profile is in 1 second.
1 second.
Yes. Right. So then it is a very fast phenomenon. So then how do you do it? For so many particles put together, like she got confused when we just said like take away the coins so quickly. When you had got sufficient time on the table, then she could say how many tails, how many heads, right? But then you say take the coin, now you tell. So it doesn't work that way, right? So in that sense, even if the process is fast, you are focusing on one photon. Right, you are focusing on one photon, and then for one photon when you are focused, right, you are able to trace the decay profile.
Only that photon.
Only for that photon. Can we go back to the board? Rupesh, you can come on this side. Right, so I'll rub this. Yeah, where did I keep the chalks? Here. It's running? Okay. So then, That's the importance of single photon counter. Why? Because we are doing the measurements in the time frame. Understand that? Right? And what is our interest? We are wanting to see the decay profile. This is my time, and if this is my intensity, I want to see the decay profile of my fluorescence. Right? So, how does my peak look like? Is it going to look like something like this? Answer is yes. But then how I do the experiment? I excite. Right? And fluorescence, is it spontaneous? If it is spontaneous, then it is UV visible, right? It is an electronic transition, but in fluorescence it is slightly delayed phenomenon. Right, although we are talking in the nanoseconds, see, your UV visible happens femtoseconds, 10 to the power minus 15 range. Right, almost like blink of an eye is too long an event. Right, it is so quick, 10 to femtosecond. We are talking in terms of nanoseconds. So you are exciting in the range of femtosecond, but then you are emitting in terms of nanosecond. See how big a difference it is, 10 to the power 6 difference, right? It's quite slow in that sense. So you excite, so quickly you get a peak, then you see nothing, but then you see the decay profile like this, and then it comes down, then you excite again, you keep doing it, keep doing it. Now I am looking at one photon, single photon, then my emission flux should be of sufficient intensity to be able to detect it in like diode tubes, diode detectors, right? So what's the way around would be? What's my prerequisite should be? My exciting the intensity of my exciting system, right, or source should be very high. The flux should be very high, then only I will get some relevant emission flux, right? If my absorption flux is very high, then my emission flux is somewhat measurable. I cannot do it with my tungsten lamp, right? The tungsten lamp is good when you are doing your normal fluorescence, because then your number of particles are too many, right? But for single photon, what do? I use laser. Yeah, what's the advantage of using laser? Yeah,
High intensity.
flux is very high, right? The flux is very high, right? So in that sense, right, you know, even my emission flux will be measurable if my absorption flux. So that's the reason in a TCSPC machine you won't see a tungsten lamp or something, you need a laser source, right? And in fluorescence, if you had done already quite some excuse me, fluorimetric measurements. So you have your sample, and if you are exciting your sample from here, you are measuring it 90 degree, either this side or that side, right? You don't want scattering to take over any of your fluorescence, so you measure it or UV visible absorption to interfere with your fluorescence, so you just measure the fluorescence at 90 degrees, right? So what we are going to do today, right? So we are going to see that the fluorescence decay profile for an ANS dye. Yeah, let's see if I remember the molecule right. So it is 8-anilino naphthalene one sulfonic acid. Acid I can write here, right? So you naphthalene group, it belongs to, it is naphthalene, right? Naphthalene 8 anilino, naphthalene 1 sulfonic acid, right? So of course that's your naphthalene group. Anilino, can I put here anilino, NH, and then right, and sulfonic acid, not very difficult structure to remember, right? You name it from where? Which side should I start numbering? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Is this not the numbering what you follow for naphthalene? Yeah. So it is 1 sulfonic acid, right? And 8 anilino. Right. Now what is the beauty of this dye? It fluoresces differently when it is in polar system, and it fluoresces differently when it is in the hydrophobic environment, apolar environment. And how it is relevant to our stuff, especially when you are working with proteins, right? So now you can imagine that this dye, right, it binds to an apolar environment, and you put the protein into, say, solution. So your all the hydrophobic residues and all, they are all deep down buried, right, deep down buried. Now once you start melting the temperature, this is like one of the examples I am trying to give you, and when you start melting the temperature by increasing, melting the protein by increasing the temperature, then the hydrophobic residues will be exposed, and this dye will get and come and bind to those hydrophobic environment, and it changes its fluorescence. So you actually can see the transition of the protein. Sometimes the conformational change is responsible for bringing about the conformational the polar environment of the protein. Sometimes you have a big domain, it's open, and in when the dye binds, it closes. So the dye which was exposed has now closed. So the domain dynamics also can be very nicely measured using ANS dye. But we are not working with proteins today. So we are working with solvents. Yeah, a very simple experiment is, we want to trace the decay profile of ANS, right, in different solvent systems. So of course we have more data available for different solvents, but we have some solvent systems already, right. So we have 1 micromolar concentrations being made in water. Yeah, you can show it, it's in water. Then we have it in acetonitrile, yeah, and then we have it in ethanol, right. So these are the 3 different measurements what we will do. We had made the solution 1 micromolar. Now fluorescence can be sensitive, so it can happen that once you do the measurement, right, for the very first time, you have to optimize the concentration, like any other experiment, that you have to optimize the parameters. So we started, let's say we start with 1 micromolar. It can happen that the intensity comes very low, yeah, and the detector is capable of measuring more, so you add more ANS to it. But sometimes you say, oh, it's too concentrated, so you just have to dilute it with sample and come to some reasonable concentration. So that kind of thing what we will do, right. So is it clear what is the objective for today's experiment? Yeah, so we are wanting to see the decay profile of ANS, right, using TCSPC, time correlated single photon counter. One logical question: do you think when we are using TCSPC we should be using concentrated solution? Why do you think so? You say no.
We don't need a huge sample.
Yeah. So you really want those particles to be as resolved as possible. So the dilute concentrations are good for TCSPC, right? So dilute concentrations are good. So right now we are just taken to begin with 1 micromolar. It can happen that we just hit the jackpot straight away, or it can happen that you might be required to dilute these samples even further. That needs to be seen, that we will see anyways. But you will have more data on more solvent systems. We will be doing these 3 solvent systems for today, also for the recording purpose, but then when you will see the Google Drive link, you will have more data for I think 2 or 3 more solvent systems which we already had measured, right? Any doubts so far? It's very clear, right? So we'll stop here and then we will move to the TCSPC lab, right? But before I stop here, I have to introduce to everyone who is going to do this experiment. Sonali, if you could come over.
Hello.
Yeah. So Sandesh, one of the flipping guys, the flip expert. Yeah. Mayuresh, yes, they also made some solutions, right? And the professional, the alternate professional person, Rupesh, the cameraman, if you can come in front and say yes. So that's Rupesh, right? So I hope he's in the frame. He's too far. Here. Now he's seen. That's Rupesh, right? So then Swati will be helping us with the measurement. So we'll show her in the lab. Okay. So I stop here. Can you pause it now? Right. So we are going to start the measurements, and Swati will be helping us with the measurements. She is Swati. You can say hi.
Hi.
Right. That's, and this is the machine, right? So it's very simple, right? Rupesh, you have to keep coming backward and forward. Can you open this, Swati? Zoom into that machine. So what you will see in the center, this is like the cuvette holder, right? Right. You come here. This is our laser. Now, these are the different probes of laser which defines which particular wavelength we are going to use for our purpose, right? And if you go back here, so from here the laser will be fired onto the system, and then at 90 degree in this direction we will be doing the measurements, and this is our detector. So it's a very straightforward setup, very straightforward setup. Now Swati, can you show them by removing the probe? How many different what wavelength is this laser?
405.
This is 405, and typically the wavelength what we use for ANS is 380 nanometers of excitation, then 400 to 600 range of emission, but we don't have that, right? So you can come closer. So you are using this Allen key, yeah. This is how you remove them, the laser. So 405 nanometer laser is gone. So can you show all the lasers what we have? Can I have this? Where is this 405 written?
Oh. Yeah. 405, and this is a 403 is a maxima of this.
Yeah, sure. You can keep this. Can you show the other probe lasers what we have?
Is 350.
Yeah, that's
510.
350. Yeah.
And 635, 290.
290. So 350 is this laser, which is closest to our excitation, right? Yeah. So this is 359 or 350?
350 and 359, the range.
Yeah, so 350 to 359, this the range of this laser. So we are going to use it because our ANS is going to absorb at 380. Now you have to go back to my absorption 5th semester practical video. I'll have put the link in the description, where I had explained that is it the end of the world if I don't have the exact wavelength which is required, right? Can you just fix it? So, so that
This
side
side
is
will be
going in,
to
yes. And then is there some kind of click sound which will come?
Yes.
Yeah, and then you just tighten, right? Tighten it. It's very straightforward in that sense. And this is the fiber optic cable?
Yes.
Yeah, you fix it. And there it goes. So our instrument is ready,
Yes.
right? You can close it. Yeah, okay. Now can you fire up the instrument and the software?
First
So-
you start this transformer
Yes.
because we need for this AC current and 50 hertz.
Okay.
So this will cut off all the currents and only pass out 50 hertz. Then switch on your UPS.
Okay. All powers on.
All the powers on, and here is the numbering 1, 2, after that 3, 4, 5. 1 minute, Rupesh.
So all the switches are at the back, and then 6. So you have to follow these number
These
sequence.
numbers.
And while shutting down the reverse,
Yes.
right?
Yes.
Sure. Yeah. And the computer?
PC.
Yes. So now for this video purpose we will stop after doing the water, right? So then you can continue doing the other 2 samples because we don't want the video to be too long. Because whatever we will be doing with the first sample, essentially we will be doing the same for
Same for
all
the
the other
second.
samples. Yes. So you are going to do the same on camera, your password as well?
Password
Show all.
side में, yeah.
It's taking time. Fine. So what software do we use to
Test. EZ. Time. Double click.
So you fire up the software?
Yes.
Yeah. Let's see how the interface looks like. Okay. Yeah, it's initializing, so you have to be a bit
Wait
patient.
for 5 minutes.
So it takes 5 minutes? Okay. Fine.
Okay. Start the experiment. This is all the programming and all this.
So we are good to go?
Yes.
We are good to go? That's good.
This is the IRF
Yeah.
and this is for your samples, decay samples.
So you can overlay all the spectras here in over.
Yes, yes. Just a second.
So, yeah, of course. So we definitely have to measure the decay. So you have to measure the decay. Yeah.
Settings. In that you change this peak percents. That's mean all the decay, matlab, how much proton you want.
Okay.
5,000, 10,000. So we put here only the 5,000.
That's essentially the flux.
Yes.
Right. So how much intensity should come from the laser? This is
Lasers.
the, yeah.
After that, just auto fit. Okay. Done.
Done. So we are good to go.
Yes.
Can you show them the cuvette?
You want this.
Can I? show them here. Now see, this is how the cuvette for a typical fluorimeter also would look like. So it is clear from all sides. A UV visible will be graduated on one opposite pair of sides, because you may see excite from here and then you measure the emission from this side. Here you are exciting from this direction and you are measuring at the 90 degree. So if I put it in the same orientation as the machine, so once the cuvette goes into that cuvette holder, then the beam is going to come on from this end, and then it is going to, we are going to measure at the 90 degree, because that's where our detector goes, from here to over there. Can you show on that side the detector, Rupesh? Yeah, so that's our detector. Okay, so we have to just clean the cuvette and put our sample in, the first sample. Yeah.
संतीश, फ्लोरेसेंस का एक और क्यूबिट रखा, वहाँ से लेके आइए ना, क्योंकि मैं इसको आईरफ के लिए यूज़ करती हूँ.
Right. So we use another cuvette, so you can put it back. It's essentially like this only, right?
Yes.
The other cuvette also?
Yes, it's same.
Yeah. So we'll wait for another cuvette to come by. Let's close it and keep it. Right, so we are good to do the measurements. So this is like one of the fluorimetry cuvettes what Swati has in her hand. So you have to really make sure that you are holding the cuvette from the
Edge of
sides, the edge, right? Not like this. So you are not wanting to have any of the organic impurity or your fingerprints to spoil the cuvette. You are going to hold it this way, because your even fingerprints are going to interfere with the fluorescence, right? And when you are going to do the measurement, can I have some tissue? Yeah. So you are going to hold it from the top, here diagonally. You are going to hold the cuvette diagonally, and then you are going to wipe it. And you are not going to wipe it this way. You don't want any of the fibers to stick onto the cuvette. So you are going to wipe it in one direction, like this. Yeah. Be gentle. Yeah. Guys, be gentle like your girlfriend, and vice versa. Right? So it has to be that way. So in one single fashion, you have to wipe it. Not up and down, but then say go in a very smooth fashion that way. So you don't need any of the particles to be sticking onto the cuvette. Right? So now we are going to put sample in Swati's cuvette. She is ready. So the capacity for these cuvettes is like 3 milliliters, the minimum sample volume required. Yeah. So our Sonali detector is putting the sample through. Yeah. Okay. No air bubble should be there, right? So Rupesh, focus on the cuvette. There should absolutely be no air bubble in the cuvette. It's a big disaster for your fluorescence, right? Now I am going to lift the cover, and we are going to put it. Now you have to make sure in which direction you have put the cuvette. For all the other experiment also, you have to put it in the same orientation, right? So it's closed. So I'm going to put the other cuvette back in, because we don't want to drop anything on the floor. Yeah. And then
Go to instrument.
yeah. So now this is the laser what we are getting from the probe, right? The laser probe what we have right now. So it's saying some 10,000 counts, right? And this is what the blue bar which you are seeing, the appearing and disappearing. It has disappeared again. So it is like one. It says the 1%, 7%. But the minute it goes red, that means you're absorbing too much. Your sample is too concentrated. In that sense, number one, you could dilute the sample. Number two, you can use the filters, which allows less of the emission to go to the detector. Can we show the filter, Swati? What are the two different kinds of filters we have got? What is this filter?
ND1.
ND1. What does this filter do?
It's cut off only the 50% of your what? Intensity of your laser.
Right. So this you put in front of the laser, right?
Yes.
Right? Not in front of the detector.
You can use both sides.
Both sides, right? So if you want your sample to be exposed with less of the laser, you can put in front of the laser.
In front of the laser.
If you want less to come in front of to the detector, then you put in front of the detector. Can you put one of the filter and show them? How do you do it? Do I have to lift the cover? Yes.
This side is for laser.
So there is a slot, I suppose.
Yes.
Yeah. So there is a slot. So you had put it already? Yeah. So there is a slot in which you just slide that filter, right? And see now once you come back to the screen, Rupesh. Now the intensity which was absorbed by the sample has, let me put the cover back, right, is reduced. Okay.
Water absorbing नहीं कर रहा है.
It's almost nothing is coming out, right? So we can remove
Filter.
because our concentration were good enough, so we don't need to use any filter for today's measurement. So we are using 1 micromolar, so it's good. The whole point is, so there is a click button here. So if you would see here, so and this lid is quite heavy. Once you put this lid, it makes a click sound, and then your instrument recognizes that the lid is closed and it has to start measuring. Right? Fine. So see this blue bar, it keeps coming and going. If instead of blue it changes color to red, then you have to do all these provisions. Either number 1, reduce the concentration of the sample, or number 2, apply filter either in front of the laser or in front of the detector. You have to optimize for your sample. Is that right, Swati?
Yes.
Okay, lovely. Can we do the measurement for this? So we are going to, so the measurement, so the emission spectra for ANS is 400 to 600.
Okay.
So we are going, we now have to select the wavelength at which we are going to see the decay, right?
Decay.
So let's say we select at 480 nanometers. Can we do that?
Just change it.
Yeah.
Click here and change it. 480. Apply.
Apply. Okay. Then you have to go to the other screen, and you have to also select the slit width, right? And that is called as band pass here, right? Can you increase the slit width? The maximum is 12.
32.
32. So you will see some significant measurement once you do the bigger slit width, right?
Yes.
Okay. Can you go to the other screen for measurement? Data.
Yes.
Yeah.
Play.
So now you have to select the decay. This is what we want to do, and then can you do it? Now the first sample we had put in is water, so we don't expect anything to light up in water. If something is lighting up in water, then I think we have to blame it on Sonali and Mayuresh, who had made the sample. So you pray, both of you, that nothing lights up. Right? Yeah? Can you see anything? I really wish something lights up. No.
Pure water.
That's how it should be, right? Pure water. If something lights up, then we start the blame game. You will be in the firing line, both of you. What did you make? So it looks like you are saved, huh? It's quite flat here so far, huh?
Yes.
Right, Swati?
Yes.
So they did a good job. What do you say? Both of them? No? How much time does it take for one scan to finish?
Depending on the concentration of your floor, height of peak. तो इसमें बहुत ज़्यादा टाइम लगेगा, तो मैं इसे क्लोज कर सकती हूँ.
You stop it if it's flat. You save it as water.
No lifetime. 0, 0, 0.
0, 0. So everything is 0, 0. Good. Congratulations. Good job. So the what you save it
सोनाली आ
as
जाइए,
water.
आप उसमें एडिटिंग कर दीजिए आपका जो सैम्पल्स था। यहाँ से नहीं होगा, वहीं से होगा
वो
आपको, क्योंकि
keyboard.
कीबोर्ड यूज करना होगा।
वही yeah.
है मैंने क्लिक करके रखा।
water decay, that's good name. Yeah.
ओके,
Okay, so now we are going to take the first sample and then we will stop the recording. Yes,
योर मेजरमेंट न्यू डीके।
right. So then can we take the cuvette out? Yeah, so do we have the beaker to throw things? No, we don't have. Okay, so this is what we are going to do. So we are going to measure the ANS in water first. So only water we did, and it was quite flat. And then we want to see if we are putting ANS, this dye, in water, then what is it? Now water being the very polar solvent. The relatively apolar solvent what we are going to use now will be the ethanol for the video purpose, but for the experiment purpose we definitely have more sets of solvents available with us. The data will be made available to you in the Google Drive description given below the video. Shall I put it? Yeah, so you have to clean the cuvette again gently, hold it diagonally, repeating again so that you don't forget, and I am going to put it in the holder, gently leave it, right, and then we are going to put the lid back. Yes, now you can see here, see, still not much of the intensity. Now if you would see, this is like 0.01%, 0.1%, 1%, and like almost like close to 8% or whatever it is. If you go too high in the signal, then it will start turning red. Now can you open the complete one? Yeah, so the band pass is at 32, so that is the maximum slit width is open. So this is the maximum say signal what we are getting from the ANS in water. Now if you had noticed that sample was yellow, when I will take it out I will show you again that it is so concentrated that it has started looking yellow. Can we do the quick measurement? Now we are going to see it at 480 nanometers, right? So 400 to 600 is the range in which the emission spectra comes for ANS. So we are seeing the decay at 480 nanometers. You keep measuring, so far no signals are coming out. So you can see it is almost like water, right? Almost like water. This is the signal, right?
Yes.
So it's pretty much flat. So we'll measure it for some time so that we have some comparison. Yeah, so nothing is shooting up from the baseline, so it's okay.
Shall I stop?
Yeah, you can stop it. Yeah.
0, 0, 0.
Yeah, everything is 0, 0, 0. So this is how you had got for water. Is that right?
Yes.
Correct. And we save this as ANS in water decay. Yeah, edit. So ANS water. Yeah. Okay. Okay. So now we can remove the cuvette. So I can show you against the background of this tissue. See? Are you getting this yellow color, Rupesh? Yeah, so it is so concentrated. Now I'll hand it over back to Sonali. You can put it in the stock solution. And now we are going to do the measurement in ethanol. Right? Yeah. Okay. So you can wash the cuvette with ethanol. Give a quick wash. Yeah. Okay. So then we are putting it in ANS in ethanol. Yeah. So you just have to make sure that at least 3 ml is there in the cuvette. If it is more, then it doesn't matter. So you have to reach up to the detector height. Yeah, the incident level slit height and the detector slit height. You have to reach there. Yeah, so I'm holding diagonally and then I'm cleaning all the 4 sides from top to bottom. This prevents any fibers sticking onto the cuvette. Can I put it? You have to go gently into the system. Yeah, and put the lid back in. Let's see what do we get. Yeah. Now this is what I meant going right. So right now you get a signal where it's green. Now if it is too concentrated, then this bar will run away towards the right side, and then this circle will start showing as red. Yeah, so it is showing 0.05%, 2% being the maximal limit of this detector. So we are pretty much in the range. Yeah?
Yes.
Is this a good signal? So our expert says yes, so we go ahead. Yeah, now you see, right? Now you see some signals. Yeah. Can you see the decay? It goes up and then slowly it goes down like this. So we have to allow it to come to the baseline, right? So it looks like a comet, pretty much like a comet tail. So this being the tip of the comet, but then as and when you are measuring, so it is clarifying. The data is clarifying a bit. So we wait until everything stabilizes, and then let's see what we get. Measure it for sufficiently long time until it reaches to the baseline.
5,000.
Yeah, you should see a nice curve going like this. That's the decay, the exponential decay curve, what you should see. So that's pretty much the top bit of the decay. Yeah, and then this is how it should go. Actually, it looks much better on the video, right? On the phone, it looks much better compared to on the screen. Yeah. Now remember, for only water and ANS in water, it was flat. There was no signal. But now, as you would see, of course, you start from a top bit and then slowly it is decaying like this. Huh? So this is the time. So we had waited for like so far 90 seconds.
No, this is not the time. Here I am just setting the peak counts 5,000. After the 5,000,
You stop.
yeah,
Yeah. Where do I see the peak counts?
here.
Okay, so it's 200 right so far. So you wait until it does the 5,000 peak counts. So it's going to take some time.
Yes. आप pause कर सकते हैं.
Yeah, it's going to take some time.
15 minutes लगेगा.
Yeah. So so far it has reached
250.
250 counts. Yeah, it's going the count over here, and we have to wait until it reaches 5,000 counts. So it is going to take some time, right? So the raw data we already had measured, and it's available in the Google Drive, so you can download the data and start the analysis. But this is what we are also going to do for ANS in acetonitride. Right, so for my video I'm not going to wait for another 15 minutes just to make the video more condensed. So how the rest of the profile for the curve looks like, you can plot it and see it for yourself. It will be an exponential decay. You already have got some flavor how the curve will look like, right? So eventually it is going to tail off and going to be closer to the x-axis, parallel to the x-axis. Yes. Right then, so I will stop this video here. So I'll sign off. Yeah. I'll see you with another experiment next time. Until then, goodbye. Take care.